All right, so yeah, welcome everyone to this year's Climate Change AI Summer School and the tutorial for the transport lecture. The topic of today's tutorial is to predict mobility demand from urban features. It's a tutorial that was initially developed by Konstantin Klemmer and Shafat Rahman. And this year, Florian and I further developed it and will guide you through it. Maybe for quick context, we can quickly introduce ourselves. I'm Felix Wagner. I'm a fourth-year PhD candidate at TU Berlin. And maybe Flo, you want to introduce yourself as well?
Sure. So hi, I'm Florian Nachtigall. I'm also a PhD candidate at TU Berlin in the group of Professor Felix Kreuzig. And we are both mainly working on decarbonization of urban transport with spatially explicit methods and some machine learning here and there.
Nice. So today's table of contents is that I will start and I will give you a quick overview of this tutorial. I will quickly give a background about the climate impact of this work. We'll highlight basically what background you need for this tutorial, what the software requirements are, and then we will dive into it. We will look into the data, analyze it a little bit, and then Flo will take over when it comes to the machine learning part. We will have a linear regression model, a gradient boosting decision tree model, and a graph neural network. And we will compare those models and in addition, discuss basically our analysis. We will discuss the takeaways we get from our analysis, the limitations, and also have a look at the explainability. So how can we interpret the prediction of our models? We will derive some policy advice and discuss further steps. We also have some tasks developed that you can try out, where you can basically code. And in the version you will see there will always be first a blank cell where you can fill in some code, and underneath it there will be a solution that we will provide for you. And of course, in this recording of the tutorial, we will also discuss the solution with you. For background, as I said, we are investigating the relationship between urban characteristics, such as the location of different points of interest in the city, of different shops or services, and bike sharing demand. The data that we have for this is real shared bicycle trips in Shenzhen, where we count the number of trips ending and starting in each neighborhood of the city. And we also count the corresponding number of points of interest, such as medical services, transportation services, etc., and see how well we can predict the number of trips ending in a specific location when using the points of interest as features. The climate impact of this is that studying bike sharing data can help us to better understand where we can allocate for example, new bicycle stands in the city. It can help us to understand where demand is in the city. And by doing all of this, we can try to kind of shift travel behavior from more carbon-intensive modes like cars towards more active modes with low carbon emission impact, such as bicycles. The background for the tutorial is that it would be good if you have a rather basic understanding of data processing and cleaning. And of course, it would also be handy to have some previous experience working with spatial data, which has coordinates such as latitude and longitude coordinates. But we will also explain all of this to you while we go through the tutorial. From the software requirements, we have a number of libraries that we're going to import. You do this by just listing them here and kind of running the different cells for everyone who hasn't done any work with code. what we can see here is that we have certain libraries that you usually use when analyzing data, such as the pandas library, but we also have more specific libraries for machine learning, such as the sklearn library or the XGBoost library, as well as libraries to handle spatial data, such as the GeoPandas library or H3Pandas. Once we've loaded all of this, as well as some libraries for the graph neural network, we can then go into our data. I'm not clicking on all of this as I've previously run all of this, so I don't have to do it again. And I will just kind of run the cells where we actually do some analysis on the work, on the code. So the data description, we have a number of different data sets that we need for our analysis. We have some shape files that contain basically the locations of different points of interests in Shenzhen. We also have a Excel file that has a translation of the points of interest, because the data is from China. The original data is all in Chinese, and we can use this Excel file to translate the data. We have trip data from 2021, and we have additional files that we can use for further analysis. The following code is taking a bit of time, because here we're going to download the data, which is stored in a Google Drive folder. You can also click on the link in order to inspect it. I've already loaded all of the data into the Google Colab, so I'm going to skip this part here. And we are also unzipping some of the files as they are in zip format. Once we've loaded all of this, it's finally time to basically load the data into and inspect it. And the first thing we're going to do here is that we basically load our trip data from the Shenzhen into a pandas data frame. We are doing this here. This was also taking quite a bit of time, as the shared bike data, like the file here, the 211000w.csv, is quite large. So I've previously run it. It takes 45 seconds on my machine. And once you have that, we can analyze this data frame. So I'm going to click on it. It will load. It will take a bit of time. Once we have this data frame, we can then go into it and see what columns we have, how many rows we have, and we will do this in the following with the count function. So this might take a bit. Let's wait a couple of seconds. I think in a previous run it was around 45 seconds. So we loaded it, and now that we've loaded it, we can use the count function to inspect the different columns and how many entries we have in each column. And what we can see is that it's super large. It has in each column close to 10 million entries. And what we can also see is we have one column named called unnamed. We have an ID column. We have a start time of a trip and an end time. We have a start latitude and longitude, as well as an end latitude and longitude, and a user ID. As it takes quite some time to work with that many entries, we will only work with a subset of the data. We will only take 100,000 entries, and we choose this data randomly by using the sample function. And then we're going to have a closer look at our data frame via the head function, which basically gives us the first 5 rows of a data frame. And as said earlier, we have a number of different columns with locations, as well as with IDs and with start and end times. And we can also, again, inspect the range of each column by using the min and the max function. And what we can see here is, for example, that we have n times between the 30th of July and the 7th of August. We have start latitudes between 0 and 47 and start longitudes between 0 and 132. And one thing that we can directly notice here is that we have some locations, some trip start or end points with 0 coordinates. However, Shenzhen's location or the longitude range is approximately between 113 and 114. That means we have some wrong measurements in our data and we need to clean our data. We do this in the next cell where we basically create a boundary of longitude and latitude range, and we filter all the data that lies within this range. And once we do this, we can again kind of look at the min and the maximum of each columns. And what we see here is that now in the start latitude and the start longitude, the minimum values are at 113 and the maximum at 114. We can also see that our overall count reduced quite a bit, but with this, we basically ensured that all of our data lies actually in Shenzhen. We can also have a more in-depth look into the temporal dimension of our data. As you might know, that obviously trips with bicycles are distributed over the day, and probably there's some more trips in the morning peak when everyone commutes to work, or in the afternoon when everyone comes back from work. And because we have a time column, the start time and the end time, we can actually analyze this. So what we do here is that we first need to convert those start and end times into something the pandas data frame can handle. And then we basically try to plot first the distribution of trips over the week, and afterwards the distribution of trips over a day. And what we can see down here in this plot is that basically we have a slight peak on Saturday of trips, but they are fairly equally distributed over the whole week. And on the right side, when we look at the distribution of trips throughout one day, we can see that we actually have this peak in the morning where lots of trips are done, as well as a peak between around 5 to like 7 or 8 o'clock in the afternoon. And of course, this information is quite handy because we when we want to then later look into like what can we actually derive as policy advice or as urban planning advice from this, is that of course we are interested in those peaks of the data, and we want to satisfy this demand, and that's what we can learn from this like temporal distribution here. For some further analysis, we can then also add as an additional column to our data frame whether a trip was done on a weekday or not. We use the day of the week function here, and then again we inspect our data again with the count and the min and the max function, and see that we now not only have the weekday as a string, but also the hours of the day and the weekday, whether it's on a weekday or not. As a next thing is that now that we've analyzed the temporal dimension and we've understood how trips are temporally distributed through the week and also through a day, we can now look at the spatial dimension. You've seen already that we have those coordinates, and we can now actually analyze them in more detail. So the first step we're going to do here is that we're going to analyze we're going to load the shapefile that is showing us Shenzhen. The shapefile you can find them here under this link. And then we use basically the plotting function of GeoPandas in order to plot the Shenzhen GeoPandas data frame. Maybe for anyone who hasn't worked with GeoPandas, it's fairly similar to a pandas data frame. The only difference is, so we can also have a look at it. Is that we have a geometry column that basically includes, in this case, for example, polygons, which we are plotting down here in gray. So those are the different polygons here of Shenzhen that you can see in this map. We can now, once we have this map, we can now overlay our trip points onto this map. And in order to do this, we first need to create GeoPandas data frames out of our original data frame that we loaded, the DF. We do this here for the starting points as well as the end points. So what we do is we basically input the data from the data frame. We create a geometry out of the latitude and longitude data, and we assign a CRS to the data. So once we have that, we can then analyze this again in a plot. Here we are plotting both the starting locations and the end locations in two subplots next to each other. So on the left, you can see the start locations marked in blue, and on the right, the end locations marked in red. What is quite interesting here is that we can already see that the distribution spatially looks fairly similar between start and end points. And that's because the bike sharing data actually is from bike stands. So people don't leave their bike anywhere in the city, but at predefined locations where those stands are. We can then also load our points of interest data. This data is saved here in this Excel file. So what the first thing we do is that we basically load the different categories of points of interests and their respective, so they are given in the original data as in Mandarin, but also given here in this file with a translation. And what we can also see that this POI data is basically divided into like larger and smaller categories, but for this tutorial, we only assume that we only are interested in the bigger categories. So once we want to, so in the next step, we basically want to analyze which categories do we actually have. We do this by dropping all the duplicates of the category column and printing its values. And now we want to load the respective shapefiles that contain the geometries for those different POIs. And when we look into the Google Drive folder, we can see that the actual shapefiles have a slightly different naming. So in the next step, we're going to clean those names that we have in the original Excel file by replacing certain characters. So we are actually replacing the flow, how's it called? It's not a tab, the space between the two strings. And for the next step, we then going to focus only on a certain subset of POIs. We assume, for example, for this tutorial that we are only interested in medical and transportation services, as well as in sports and recreation facilities. So we kind of set those three POIs of categories of interest, and then we're going to load the different shapefiles. This here is what this code basically does is it goes into the folder where the shapefiles lie and loops through all the different paths that are shapefiles and only takes the ones that correspond to the 3 categories we defined earlier. And we then concatenate them to one GeoPandas data frame. And what we can see is that we basically have 80,000 POIs, and we have 3 different POI types. And as a next step, what we can do here, this is quite a nice feature of GeoPandas data frames. It's a function called explore. This is a function that Flo and I are using quite frequently in our work. You can basically do this with every GeoPandas data frame, which has a geometry. You can give it a column as well as an underlying map, and it then plots you all your data on an interactive map, so you can easily explore where certain locations are, in our case, where those different POIs are, and you can even like inspect them further and analyze, for example, which value it has. And for further analysis, we're gonna store our data so that in case we're gonna take a break in between or we come back tomorrow to this tutorial, we don't have to like define and run all of the code again, but we have actually the POI GDF already stored as an individual file. Now we come to the methodology. So just to recap quickly, what have we done so far? We inspected our trip data. We inspected the temporal dimension of it. We also inspected the spatial dimension. We did this with GeoPandas data frames and plotting of GeoPandas data frames. And after that, we looked at the POI data. We selected only a subset of POIs, categories that we are interested in. And then we used the explore function to look at the POI data on an interactive map. Now we move further towards the machine learning part. And as the task that we are trying to solve here is that we basically want to investigate the influence of the presence of points of interest on trip destinations of shared bikes. And in order to do this, we first need to kind of count the number of POIs and number of trip endings in every location. And in order to do this, we're going to introduce a grid. And then for every grid cell, we basically calculate the number of trip endings and POIs. And we use here the H3 hexagonal grid. It's a grid that was developed by Uber in order to kind of sum up the different POIs and trips. And H3 is actually quite a nice library because and a nice system because it's a unique indexing system for the whole globe. So you have a specific ID that always corresponds to the same location. And it also has a number of different spatial resolutions. So if you're interested, check this out on the link here. In our case, we are using the resolution 8 that corresponds to a grid cell area of around 0.7 square kilometer. And the first thing we're going to do is, in order to analyze this, is we're going to create a trip data frame from the trip destinations again. We then going to aggregate using the Geo2H3 aggregate function from the H3 pandas library. And we aggregate those point geometries per hexagon grid cell and count them. And once we've done that, we can again use the explore function in order to visually inspect the density in each hexagon grid cell. So what we can see is basically that in some locations we have higher counts, like here we have 464 counts, or here in yellow we even have 791, and in other locations we only have 1 or 2 counts. And we then do the same thing to our points of interest data. And we do this for all of our three categories. And again, we have such a hash that basically is a unique identifier of our hexagon grid. And for each of those hexagon grid cell, we get a number of PYs for medical service, sports recreation, and transportation service. And the final step, and then I will hand it over to Flo, is that as in our analysis, we only want to consider grid cells where we actually have shared bike stands. We have to filter our data, so we only basically take grid cells where a trip ends, and the rest we fill up with nans. And with that, I would hand it over to Flo. And of course, if there's anything missing, I will try to, and it comes to my mind, I will jump in later. And yeah, with that, Flo, feel free to continue.
Great, thank you. Are you quit like share my own screen, right?
Yes.
All right, so let's continue. So now that we have the counts in each of trips ending in each location and the number of POIs in each location or in each grid cell, let's see if we can find a relationship. So we will try out several methods to inspect this relationship and at the end discuss the pros and cons of each of them. Let's start with a linear regression. So a very simple regression, which assumes a linear relationship between the number of points of interest in a location and the number of trips ending there. So if I run this cell, as our well, let's see what happened here. Counts the trips. And okay, we have our linear regression. So as an independent variable, we use the number of points of interest. And as our dependent variable, we use the trip count. So we do here for the first iteration, we do the separate linear regressions, and the coefficient of the linear regression can be interpreted as the increase in trips ending in this location with one additional sports recreation facility or one additional transport service in that area. So one more transport service will lead to an estimated 2.8 more trips ending there. And we can also combine those three features, and you do a single linear regression with all of them. And we will see that the coefficients are a bit lower, but overall we have an R squared of 40% of 0.4, which is often interpreted as that the method or the regression can explain 40% of the variability in the dependent in the outcome, so in the number of trips ending there. But because we don't know whether such a linear assumption between the number of points of interest and the number of trips is appropriate, we want to try other methods which don't make such strong parametric assumptions. So for example, let's use a gradient boosting decision tree. So that is great for modeling threshold effects and generally non-linearities. So that's also our first task here. So we will use an XGBoost regressor, so as indicated here. So let's see if I can get some auto-completion here. Yes, so we will instantiate the model, then we will fit the model, and then we will predict. So we do model predict, and we use our independent variables to predict our target. And then we calculate the R square again based on our prediction, similar to how we did it for the linear regression. And let's see how much of the variability the model can explain. Well, it explains 95%, which seems like a lot. Well, it is a lot, but this result has to be taken with a grain of salt. because a machine learning model, if it has enough parameters, if it's complex enough, it can theoretically fit any kind of data distribution. So we'll talk more about this later, but there could be a problem with overfitting here. So let's keep that in mind and move on. And the third model we want to try is a graph neural network. So why do we want to do that? Because for the XGBoost, while it's able to account for nonlinearities and threshold effects, it doesn't have any idea of the spatial component of the data, of the spatial relation, that two locations being close to one another, the points of interest in one location might influence the trips ending in the other location. And while we could also add features to account for kind of this spatial spillover effects, so for example, we could include the number of points of interest in a buffer around a bike stand, but we can also use a graph neural network, which from the model already is able to account for this kind of spatial interdependencies. And we use PyTorch to implement the graph neural network, just really a standard way of doing so. So we again have our independent points of interest data, our dependent count. We will transform the data, convert the data into so-called PyTorch tensors, which is just another way. It's in just an internal data representation format similar to a NumPy array, just specifically for tensor. And then we will create a graph. So a graph describes which cells in our case are close to one another. So which cells are in the neighborhood of one another, and then the model learns kind of the interdependencies between the proximate cells. So let's run this, and here is our graph neural network. So we have essentially 3 layers. We have 2 graph convolutional layers, and then 1 fully connected linear layer at the end for just the prediction making. And optionally a dropout layer. So that's very straightforward implementation, and using the PyTorch geometric library, this is great because really we don't have to implement the graph neural network ourselves, but we can just reuse the layers which are provided by the library. So we specify the hyperparameters for the fitting, for the training of the model. So the number of epochs, which refers to how often do we feed all the data through the network in order to minimize the loss function and in order to kind of detect the patterns in the data. So we pass all of our data 1,000 times through the network. We choose a learning rate of 0.01. And we will print out kind of the loss or the error during the training for every 100 epochs, so we can kind of monitor how fast the model learns. We use an Adam optimizer, which is kind of a standard. Just to illustrate it here, we have our training loop where we iterate through the epochs, and as I said, every 100 epochs we kind of print out the error. So as we can see, the loss decreases quite a bit, and when we compute the R² of the model, we also see that it is able to capture some kind of relationship between the number of points of interest and the trips ending there. It is lower than from that of XGBoost, but a bit higher than that of the linear regression. But again, for now, let's take it with a grain of salt. We will discuss how generalizable or how robust these results are later. But for now, let's have a look at how this looks spatially. So for the kind of the ground truth distribution of trip endings, as well as for the linear model for the XGBoost and for the graph neural network, we plot the predictions here, and you can see, for example, that for the graph neural network, it's more spatially smooth because it knows the kind of the spatial dependency in the data. So like 2 locations close to another will probably get a similar value, whereas for XGBoost, those 2 locations are treated as really independent samples, and so the predictions are less smooth. We will also look at the error. So kind of the residual between the prediction and the true value, and to check if there are any spatial patterns. Ideally, there are no spatial patterns. That means that kind of the errors should be independent from one another. And for these three models, it actually looks that way. So that is great. We don't see kind of any cluster of high errors or low errors, which would indicate that we probably did something wrong, or we don't account for some spatial effects, which we should account for. So, but now I've said 2 times that we have to take the training R squared with a grain of salt. Why is that so? So for machine learning models, if they are complex enough, they can theoretically fit any kind of data. So just imagine for the XGBoost, for a regression tree at the end, if you have just 100 samples and like multiple regression trees with let's say 100 splits, you can essentially kind of, by having so many splits, you can fit each data into a single leaf. So essentially perfectly fitting all the data and just memorizing which dependent and independent variable belong to another. So what we have to do is to evaluate the model on data it has not seen during the training. So it's kind of called an auto sample or generalization performance, which we're interested in. And that is really important to understand whether the model actually learns something and really understands kind of ideally the causal relationship, but at least the correlation between the independent and dependent variable, or if it's just memorizing the data. For the linear regression, this is less important because due to the strong parametric assumptions, there are not so many kind of free parameters which would allow to memorize the data. So the risk of overfitting, as it's called, is very small, whereas, or it's not there, whereas for the machine learning model, it is an issue. So we will split our data in 3 ways. We will split it into a training set, a validation set, and a test set. So the test set will be used so that it will be 20% of the data will belong to the test set, 20% to the validation set, and 60% to the we will use for training. Why do we differentiate? Why we have like a test and a validation set? So the test set we will use at the very, very end to evaluate how well the model performed. And this data has never like been shown to the model before. So that's really untouched new data. We will keep that aside. We will not look at that. And just at the very, very end, we have a look at that. The validation data on the other side, we will use to tune the hyperparameters of a model. So let's say, for example, I mentioned the number of epochs before. This is an important parameter for training a neural network, because if you have too few epochs, like you may not be able to extract all the signals, all the patterns in the data and kind of stop training too early. But if we train too long, well, it's a waste of computational resources. We might overfit to the training data, and kind of detecting what is a good learning weight, what is a good number of epochs, or like for the XGBoost, a good number of tree depth or a number of tree estimators. We need kind of a separate set of data on which we can kind of validate that, essentially, tune our hyperparameters. And we don't want to do that on the test set, because otherwise our final evaluation is not on data the model has never seen, but we've already used that data to train hyperparameters, and that may lead to over-optimistic prediction results or prediction estimates. So we use the test train split function from the sklearn library. Actually, we do it twice because it just splits it in 2, and we want to split it 3 ways. So we do it twice. Let's visualize the grid cells, which belong to test, training, and validation sets. So you see it's just a random split. So there shouldn't be any spatial pattern visible here. And most of as you can see, 60% are blue, so 60% are used for training. So let's come back to our 3 methods. Let's use the linear regression again and look how close the train and the test R squared are. And they are really close. So could also be that the test R squared is larger, could be that it's lower. Anyways, this is really close to one another, so that's great. As I said, overfitting with the linear regression is not a thing, so that's really nice. Let's look at the XGBoost method. And here we see, as I mentioned before, like we have a super, super high training R squared. So essentially the model memorizes the data, whereas the test R squared is dramatically lower. So we are completely overfitting here. And let's see how that looks over time. So we here now plot kind of the number of trees, so kind of the learning progress during training. So we start here, and we will see that we see the root mean squared error, and that it decreases at the very beginning for the first trees added, and then at some point only the training error keeps on decreasing, and the validation error increases again. So right about here, where the training and the validation error increases again, we start to overfit. Let's have a look at, so what we could do is abort the training right here, or maybe try out a smaller learning rate. So there are different ways of approaching this problem, but this is definitely problematic, and we will tackle this later. So let's look at the graph neural network, if that is showing similar problems. So we also see here again that the training loss decreases, and we see that the validation loss first decreases and then kind of jumps back and forth a bit. So we'll see that in a moment spatially. So we also see here, okay, the test R squared is even negative. So it really doesn't capture any kind of relationship in the data. It's just purely kind of memorizing the training data, and it's not able to generalize. This because we're only using a small sample. If you try it with a different seed, you might have a positive R squared. So it's just really noisy, but it's always much lower than the training R squared. That is for sure. So if we visualize that, we see really that similar to XGBoost, the training error decreases while the validation error starts to increase again. And it's actually really noisy. So it really jumps up and down. And that is a clear signal that the learning rate is too large. So it's not able to find the minimum, but it's really jumping around over the minimum. And then actually, yeah, not converging to a stable loss. So let's take one step back and recap what we've seen so far, and recap the R squareds. So for the 3 models retrained, we saw that all of them kind of fit the data well during training, but the XGBoost and graph neural network actually struggle to predict on unseen data. So here we are clearly overfitting, and the linear regression does well. So what are our main takeaways from the model comparison so far? So linear versus nonlinear relationship. Often machine learning always sounds so cool and exciting and powerful, but this it comes at a cost. So it's much more complex to train such a model. There's a risk of overfitting, and one needs to be careful. And if the data has a linear relationship, if it's reasonable to assume that, for example, our points of interest are linear correlated to the number of trips ending there, then sometimes machine learning is not the best choice, but a linear regression will do the job and is even more robust. In our case, it's hard to argue. I think there's a good intuition why there could be a linear relationship, but there could also be threshold effects that after some point, like there are just not more people going there. Then there are other factors like bike infrastructure locally, which also probably have some threshold effect. These kind of features we currently don't take into consideration. So it is because we only looked at a very small sample. I don't want to draw any conclusions here which model will definitely be better when we kind of tune the machine learning models better and avoid the overfitting. But we will see that in a bit. And then let's talk quickly about model complexity. So deep learning graph neural network can be seen as a deep learning model. It can have quite a lot of parameters which need to be tuned, and that requires a lot of data. And especially if data is scarce, sometimes such a complex model is not the best. Sometimes a more simple model like XGBoost, which requires way less training data, is superior, both in performance and the risk of kind of overfitting. So that, and for several competitions on, for example, what's it called? Kaggle, I think. Yeah, have shown that then on tabular data, XGBoost and similar methods like GM like GBM, sorry, and Cat Boost and also Random Forest perform very well and often perform better than deep learning methods. But of course, it really depends on the task. For non-tabular data, often deep learning is great. And then the last point I want to highlight is choose your hyperparameters wisely. So really, it is important that you do know what's happening there, that you look at the validation laws, that you understand what the model is doing, and there's also a task here that to play around with those two models a bit, because there is quite a lot of room for improvement. So what are we doing? We are trying to improve the predictive performance, so the test R squares of the graph neural network by tuning its hyperparameters, and also implement early stopping. So early stopping is a concept that says that after a certain time, when there is no further improvement, so no decrease in the loss during training, that the model will stop training. So we don't, if the validation just stagnates, potentially even increases again, the model training will stop to kind of prevent this overfitting. And this is a good practice, especially if you don't know kind of the hyperparameters you need very well. So that's always good to do. But before we kind of look into that, let's talk about the learning rate and the number of epochs. So we will go back up to the graph neural network and play around with that a bit. So let's keep kind of this picture. And as I said before, I suspect the learning rate is too big here because it's jumping around too much. So let's make the learning rate a lot smaller and see what's happening there. So just made it smaller by a factor of, I think, 1,000 or so. Just much smaller, just to kind of show the impact. And we directly see that the test R squared is much better. It's not yet as good as the linear regression, for example, but it's at least positive. It's able to generalize, it's able to predict on unseen data. It actually captures some information. So that's really great. Let's regenerate this plot and look how this looks. Great. It's much smoother. So the learning rate is now really small. So we don't see kind of the spikes. But what we see is that the validation loss, even to the end, kind of still is decreasing. I mean, it levels off here. So maybe we just found the perfect spot here, but maybe it could even be that it decreases a bit further, because let's increase the number of epochs or increase the learning rate a bit. So one way or the other, and see how kind of this will influence the training. And because I don't want to wait so long, so I could now double the number of epochs, but I will just, because I don't want to wait so long, increase the learning rate again a bit by a factor of 10. And then let's see. So let's keep this in mind. So it's close to 0.3 R squared. And let's see what happens. Okay, so actually it didn't improve. So maybe the smaller learning rate was better. Maybe increasing the number of epochs a bit more is better. But because if we now look at this, we see that it really kind of levels off, but we don't see any indication of overfitting here. The validation loss doesn't increase again, so that's great. So this is, we can work with this model for now. For the early stopping, as I said, the intuition is to kind of keep this validation loss, to monitor that, and after some time abort the training. So let's say we can set a number of epochs after which, if the loss didn't decrease, we will abort. So if we say, I don't know, after 10 epochs, then it will probably somewhere here or here, I don't know, it will stop the training. But I've provided some reference code on how to do this, kind of what's the intuition is behind here, but you would kind of implement this up here in the training of the model. But we will not do that right now. But so this is something you can do on by yourself. And then another thing which you can try out to improve your prediction performance of the graph neural network is to try out different architectures. So depending on kind of the data, different architectures make sense. So for temporal data, you might use a GRU cell, or you might use an LSTM to kind of capture the temporal lag in the data, and kind of for the spatial data here, this graph neural network to account for the kind of the spatial interdependency is great, and then the convolution to kind of aggregate the data from close by nodes in the graphs and to kind of account for this kind of spatial spillover effects. But there are also other layers we could try out. So for example, there is this I'm not sure how to pronounce this actually, but what this is actually it's a graph neural network layer with a attention mechanism. So maybe you know this paper, kind of attention is all that's needed, let's transform a paper. So we are using a similar kind of architecture here to and have like the kind of these attention heads and kind of look at, so to kind of point the attention at specific places which might be more important for the predictions than others. But this is something you can just try out by yourself. So there are on PyTorch Geometric, there are quite a few layer architectures you can try out. So I just highlighted these two here, which you essentially can above, where we define the graph convolutional network, you can just kind of plug them in as layers instead of what was there before, and train the model. For some, you need to adjust the training a bit. For I think these two, you can just kind of plug in and play and see what the impact on predictive performance is. But you can do that by yourself. We'll jump over that for now. Okay, so now let's talk about XGBoost. So for XGBoost, the training is usually a bit faster. So what we can do here is do a bit of a more structured, exhaustive hyperparameter optimization. So before we kind of used a bit of intuition, we looked at the validation loss, we kind of played around with that, with the number of epochs, the learning rate a bit. But this was, of course, really like manual and not exhaustive and really structural. But because deep learning networks often are quite computational and time intensive to train, trying out hundreds of combinations of hyperparameters is often just not feasible. But for XGBoost, it more often is. So let's, given the example of XGBoost, let's look at how we can kind of do this very structured hyperparameter optimization. So there are two very prominent approaches to structured hyperparameter optimization. One is called a grid search. The other is called random search. Both are essentially trying out different hyperparameters combinations and evaluating them on a holdout set and seeing which one performs best. The grid search is an exhaustive one, so it really tries out all the parameter combinations you provide. The random search is just randomly sampling and picking a few. So that is, of course, faster because there are less iterations. And depending on the use case, one or the other might be better. There are also more sophisticated, clever approaches to optimize hyperparameters, but these ones are the two most known ones, and it's good to start with them. So which hyperparameters are we interested in when we are talking about when we have a XGBoost regressor? So that's the max depth of a single tree. That's the number of estimators. So essentially the number of trees of the model and the learning rate. Again, so let's say we are interested in I think the default of the max depth is 4, could be mistaken, but let's say we try out to make the model a bit more complex. So we try out like until 10 and just have single step here. Learning rate, I think we had 0.01. Maybe let's try something a bit smaller again. And the number of estimators, I think the default here is 100. Let's do a range here again from 100 to 500, 100 kind of I'm not sure how to say that in English. So we try 100, 200, 300, 400, and yes. So, and then we will use from sklearn, from the model selection, the random search CV. Let's look at the parameters which we have to provide here. So we have to provide our estimators, our model, our parameter distribution, kind of the hyperparameter tuning space we just defined here. Then the number of iterations. So as I said, the random search is just it's not an exhaustive search, but it's just picking a few examples. So we pick n iterations essentially. And I think that's for now, these are the most important ones. So we provide our model, we provide our hyperparameter tuning space, waiting for the auto-completion. Okay, no auto-completion here. And then the n iterations. So let's say 10. And I'm not sure, maybe I forgot something. But
there's a range missing at learning rate.
No, that's fine.
Okay.
Sorry. We can just either specify the list or create a so let's see if that runs through. Of course, it didn't. Okay, let me just peek here. What I forgot here. So we provided the estimator, the number of iterations, the parameter distribution. So if we do cross-validation, which we do here, the number of kind of cross-validate, polls. And I think maybe I'm sorry. The model was the graph neural network model, which of course doesn't work here. So we pass in the XGBoost model, run the cell again. We should see some output if we specify a verbosity level, which let's do that. So we actually see what's going on here, what's happening. Let me report this cell quickly and run it again, just so you see we're fitting 5 folds for each of those kind of 10 hyperparameter candidates. So it's from this space, it's picking 10, it's like 5-fold cross-validation, that's the default. And here we see kind of which combination it chooses. We see the score, and the default score metric is R². So we see quite a big range of R² here, and that's of course always the R² in the holdout set on the validation set, I think in this case. Actually on the 5th fold of the train set, yes.
Can you quickly elaborate also what cross-validation is?
Yes. So instead of doing a simple train test split or a train validation test split, which I explained before. So splitting the data into just kind of 2 sets, a train and a test, using the one for training and the other one for evaluating the data. We could also let's start like this. What are the disadvantages of this approach? So we will only evaluate the model on this kind of 20% test data. And this, even though we pick this randomly, it might be special. It might be something like if we have geographical data of these 20% may be in a location which is different from the other 80% of the data. So and we want to understand how good the model performs on all the data. So what we can do is kind of do this test train split multiple times. Let's say 5 times. So we always have 20% testing and 80% training, but we change which 20%, which of the data we use for testing. And we do it in a way that each sample in the data is once used for testing. So it's 5-fold cross-validation. That means we have 5 folds. Each of them is 20% of the data, and each is once used kind of as a test set, and the other 4 times for training. And then at the end, we have kind of 5 R², 1 R² for each fold. We will just average them. And then that's kind of how well our model or our model specification performs on all of the data. And that's a more robust estimator than just having a test train split and just evaluating on 20% of the data. Because we just use more data for evaluation without having kind of this issue of overfitting, which we had at the very beginning, where we just trained on everything and then predicted on the same data. So that's kind of this cross-validation approach is always good. As I said, so essentially we train 5 models. So for deep learning, it's often not feasible, but here we can easily do that because you saw that went quite fast. So we increased our R² on our test data set. So that is great. So also the XGBoost is able to learn something to capture a meaningful relationship between the number of points of interest and the number of trips ending there. So let's, I think if I remember correctly, the R² of the linear regression was still higher. So I think it was like 38% or 0.38. So it seems like with the small sample of data, linear regression might just do the job, but this is too early, like just with this kind of small sample and just a limited set of features, which we just use to kind of, as for this demo purpose, it's kind of it's not a robust foundation to say which model is generally better suited for the task. But for this kind of client, small proof of concept, the linear regression performed great. So that's also an interesting takeaway. And then at the very end, let's save our model. So we are here saving our PyTorch model, so our graph neural network, and that is generally a very important thing because it allows you first to reproduce your own results at a later point in time to maybe apply the model to different data, but it's also a great practice for kind of, if you research to be transparent and that other people reproduce your results. So that's always great to save the model. You can actually save in two ways. You can just save kind of the full Python representation as a pickle, so just like serialize the data, store it, and then you can reload it. But of course, if you then have a different PyTorch version or somebody else wants to load it, it might not work. So it's often a better practice to use kind of just store the model weights, so kind of the tune parameters of the individual neurons, and then somebody else can kind of create the architecture again, load your weights, and then it is the same model essentially. So that's what we're doing here. Okay, let's talk about explainability quickly. So we just have those three features, but we don't really know. We know based on the coefficients of the linear regression which ones were predictive, but we might be interested in exploring this a bit further and understanding how specific features influence the outcome. For this specific purpose, maybe it's not the most interesting, but talking about healthcare applications, talking about other things where first you want to understand what the model is actually doing and maybe also understand what kind of drives the result. So we can use SHAP for that. So SHAP is a great way of kind of explaining individual predictions made by the model. So it actually kind of decomposes the prediction and says essentially for each feature, what was their contribution to the prediction for this specific sample. So in our case, we have those three features: the transportation services, sport and recreation facilities, and medical services. And so what we do here is we use our XGBoost model and kind of initialize this SHAP tree explainer, and then we make some nice plots. So kind of a summary plot, also called beesworm plot, which tells us for each sample. So each sample is here represented as a single dot. What's the impact on the outcome is. So a SHAP value is kind of always in the unit of the outcome variable, so in the number of trips, and that means so how to interpret this analysis. So blue means low feature value, so low transportation densities in a grid cell lead to fewer bike trips ending there, and higher number of transportation services in a grid cell lead to more trips ending there. That's very intuitive, but here it's nice to kind of see this effect. And for example, for medical service, it's a bit more mixed. We can also use a scatter plot and look at the kind of on our 2D scale. It's essentially the same, just on this 2D scale. We can see here for the transportation services, there is a very nice and very clean linear relationship. So also indicating that a linear regression might be a good choice here. For sports and recreation facilities, it's a bit more mixed and a bit random. And for medical service, it's even slightly decreasing, I might to say. So, but that we can of course make hypothesis about this, why transportation facilities might increase the number of trips ending there, whereas medical service may not. So maybe people use bike sharing as a kind of intermodal mobility. So they kind of use a bike to go to the metro and then ride the metro to some other place. Whereas for medical services, maybe if people go to the doctor, they may not necessarily take a bike. Maybe they use, because they go to the doctor, they may use another mode of transport. So there are. We don't know what the cost here is, but it is interesting to see how the different features have a different impact on the outcome.
Maybe one quick note. Maybe you can touch quickly on the topic of causality in terms of interpreting causal Shapley values, or Shapley values in general. Sorry.
So of course, our model only captures correlations. So that's very important. We, of course, don't know what actually drives bicycle trips ending in location. We just have the number of points of interest and the number of bike trips, and it looks like there is, or we see there is a relationship, but we don't know whether it's causal. We don't know whether the number of points of interest is just a proxy for something else which actually drives bike trips. So maybe people don't go to the points of interest, but there is just better bicycle infrastructure in kind of these areas because there are, I don't know, newer, like, I don't know. So there could be another relationship. There could be an unobserved confounder, which explains both the kind of the high points of interest and the high trip endings. And so there wouldn't be a causal relationship between points of interest and trip endings. So in this case, it's kind of intuitive that there is a certain causal relationship. We don't know whether it's kind of the full causal relationship we observe here. This is really just the correlation. But there could be a confounder which kind of biases this relationship. Yeah, Felix, do you want to add something? You're the expert on this topic.
No, it's just as you said. It's a really nice way to see what the model does, but deriving directly interventions from this or any causal takeaways is sometimes tricky. And yeah, just to be aware of this. And maybe one further note, as we are working with spatial data, Shapley values are also quite interesting because, as Flo said already, each dot represents a sample. And of course, each dot thereby also represents a location. And so we can also analyze those Shapley values spatially. Yeah.
So that's a great point, yes. Okay, so our tutorial is coming to an end. There is just one more task, and that's actually quite a cool task because it really kind of contextualizes why we're doing this whole thing. So we've just been talking about the relationship between points of interest and trip densities, but why are we actually, why are we doing this? Of course, to understand bike behavior, but also we could use this analysis to identify optimal locations for future bike stands. So as a kind of a city planner or somebody working in this bike sharing company, where should you build those new bike stands in order to meet demand and kind of maximize cycling in the city? And we can use our model to do that. So the intuition here is that we look just at areas where there are no bike stands yet, but high points. We look at the points of interest, a density in these kind of places, and just predict the number of trips which would, as given the observed data, which we believe to end there, if there would be a bike rack. So how do we do that? So we kind of define what our new locations are. So we don't really know exactly where the bike racks are currently, but we can use the trip endings as a proxy because, as Felix said at the beginning, the trips can only end kind of at where there's a bike stand. So let's use let's filter our points of interest counts by where there are no trips ending there. So trips was a geodata frame. The index was kind of the spatial cell ID, and we just use these spatial cells from where the trips end to kind of exclude the spatial cells for our points of interest counts. And then we use our XGBoost model to predict for these new locations. And actually, I'm lazy, so we'll just copy it from down here. So we use our 3 features again for the new locations. We predict that, and then we visualize that on the map. And trip is not, it's probably because it's trips. Yes, great. So nice. So why don't we see kind of grid cells everywhere? We only see the new locations, so where there are currently no trips ending. But there are points of interest, and the color indicates our prediction. So how many trips we would expect to end there if there would be bike stands. And we see quite a few where these kind of locations, these yellow locations, could be great potential locations for future bike stands. And maybe we want to go one step further and say, okay, people may be willing to walk quite a bit from a bike stand to, I don't know, points of interest or wherever they want to go. So let's filter these locations by locations that are far away or relatively far away, not in walking distance from existing locations. So instead of not only looking at grid cells where there are no bike stands, let's also look at their direct neighbors. So we use, again, from the H3 pandas library, the so-called hex ring. So that's just the neighbors of spatially as neighboring cells as an indicator to which locations we don't want to look at. We filter by them, so we really only have spatial cells which are not in walking distance or in close proximity to existing bike stands. And then let's plot them again. And if so, this could be a great starting point to give policy advice on where new bike stands could be created to to increase cycling in this area and generally increase cycling in the whole city. Great. So what could be the next steps? We could use all the data, all the trip data, all the points of interest, or actually we use all the points of interest. We could use all the trip data instead of just a subset, actually see which model performs best. We could use other features which we believe to be important. So for example, the local bicycle infrastructure will certainly play a role. And yeah, so these could be next steps you could do on your own. And then with that, thank you from my side. I hope you enjoyed the tutorial. Felix, I don't know, do you want to say a few more words?
Also from my side, thank you a lot. And if you have any questions, just feel free to reach out. You have our contacts, I think, at the beginning of the tutorial. And yeah, we wish you a great summer school. Bye-bye.